As in the previous lecture, let X be a connected and locally path connected to logical space, and let P tilde from X tilde to X be the universal cover. So we fix this data once and for all. So consider the following two sets. So the first is C of X. This is the covers of X. Such that Y is connected and P is a covering. Modulo the following equivalence relation, where we define P equivalent to P prime if there is a commutative diagram y naught, y prime, y naught prime to x naught is P prime, and this is an isomorphism. So the second set is the set of subgroups of odd P tilde of odd P tilde. So we first define two maps. We have phi from C of X to S of X, S of and psi from S of odd P tilde to C of X. So let us first define phi. Sorry. So given a cover P from y naught to x naught, there is a unique lift F So first we will check that F is a covering map. So let y and y be a point, and let x be p of y. So let v containing p of y be for x, let v containing x be an open set which is path connected and evenly covered by both p tilde and p. Then P inverse V is the disjoint union of yi in P inverse x, u sub yi. So u sub yi is the unique sheet which contains yi, and P tilde inverse of V we can write as disjoint union of wi in P tilde inverse of x, w of wi. So it is clear that wwi is path connected. Since V is path connected, hence f of w sub wi is contained in u of f of wi. Moreover, f restricted to wi from wi to u f of wi is a homomorphism since f restricted to wi is equal to p restricted to u f of wi inverse compose p tilde restricted to wi. So from this, it easily follows that f inverse of u sub y is equal to the disjoint union of wj inside f inverse of y w sub wj. And f from w sub wj to u sub y is a homeomorphism. Thus, for each y in y, we have produced an open neighborhood which is evenly covered by F. Thus, F is a covering. So we define phi of P to be equal to ought of F. So recall that ought of F is those maps sigma pictured in a diagram like this. So this clearly implies that ought of F is a subgroup of ought of P tilde. So next, let us define the map psi so let H contain an ought P tilde be a subgroup. Then define y naught to be equal to x tilde mod H, comma, the orbit of x naught, which we will write x naught tilde, which we write as x naught tilde mod H. Thus we have a diagram F. So we need to show that P is a covering map. So P exists by the universal property of the quotient map. So since H is contained in ought P tilde and ought P tilde acts on x tilde by a covering space action, it follows that H acts on x tilde by a covering space action Thus, using the result in the previous lecture, this implies that F is a covering map. So let X be in X and let V be a path connected open set, open neighborhood of X, which is evenly covered by P tilde. Then we have P tilde inverse of V is equal to disjoint union over all the fibers over X, W of X, X tilde I. So we already saw odd P tilde acts freely and transitively on the fiber P tilde inverse X. And from the definition of X tilde mod H as the space of orbits of H orbits, it is clear that the H orbits in P tilde inverse X are in bijection with P inverse X. Okay, that's correct. So for each H orbit, in P tilde inverse of X, choose an X tilde I in that orbit. Then we can write P tilde inverse of V is the disjoint union of I running in some index set. So this index set indexes the different H orbits, disjoint union of H in H, and H dot W xi tilde. So we have just used here that P tilde inverse of X is equal to disjoint union of I in I, H dot xi tilde. So now note that if Z1 and Z2 are two H invariant and disjoint subsets in X tilde, then Z1 mod H and Z2 mod H are also disjoint. In X tilde mod H. Thus, so using this observation and applying F to this equation, let's call this equation 1, we get F of P tilde inverse of V is equal to disjoint union I in I, F of H in H, H dot W X I tilde. So each of these thing is H invariant. And this is how we have used this observation. So this is equal to disjoint union I in I. And since we are going modulo H, so this is simply equal to F of W X I tilde. So since F is a covering map, it is open. Since P tilde is equal to P compose F and F is surjective, we have F of F inverse P inverse V is equal to P inverse V. This is equal to disjoint union of I in, this is I in I, F of W X I tilde. Thus, P inverse V is a disjoint union of open sets. To show that P is a covering, it only remains to show that P from F of Wxi tilde to V is a homeomorphism. But note that we have maps Wxi tilde F to F of Wxi tilde, and here we have P. So this composite is P tilde, which is a homeomorphism. And moreover, F from Wxi tilde to F of Wxi tilde is a bijection. Since H dot Wxi tilde is disjoint from wxi tilde if h is not equal to identity. As f is also continuous and open, this implies f is a homeomorphism. So this implies P is a homeomorphism. So this shows that P is a covering map. So thus define psi of H to be P from x tilde mod H, x naught tilde mod H to x, x naught. So the theorem is the maps phi and psi are inverses of each other. So proof: so let us first show that psi compose phi of P is equal to P. So we have a lift F uh, but recall and phi of P is defined to be odd F. So recall that in the previous lecture we had proved that if we have a cover x tilde x naught tilde to, let's say, F, where x tilde x naught tilde is simply connected Then this covering map can be recovered as a quotient out F. Now here we have map P to XX0, and one easily checks that using the property of the quotient topology that there is a map P prime, and then using a simple diagram chase, one checks that the triangle so let's say this is, let's give this map a name A, so one easily checks that P prime is equal to P compose A. Thus the covers and are equal. So this proves that psi compose phi is equal to identity. So to show that phi compose psi is equal to identity, we need to show that H is equal to aught of x tilde to x tilde mod H. But again, we had proved this result in the previous lecture. So this completes the proof of the theorem. So next, we want to show that aught of P tilde is isomorphic to the fundamental group of x at x naught. So we first define a map phi from aught P to pi 1 x x naught. So given f aught P tilde, given f in aught P tilde, let gamma be a path from x naught tilde to f of x naught tilde, and define, so before that, so then P tilde compose gamma is a loop at x naught. So define phi of f to be equal to the homotopy class of this loop in the fundamental group. So if gamma prime is another path from x naught to f of x naught tilde to f of x naught tilde, then gamma star, the inverse of gamma prime, is a loop at x naught tilde. Thus, there is a homotopy f between the constant loop at x naught tilde and gamma star, the inverse of gamma prime. Thus, P compose f, P tilde compose f is a homotopy between Cx naught and P tilde compose gamma star P tilde compose the inverse of gamma prime. Now the Cx naught represents the identity element in the fundamental group. Thus, the identity is equal to the homotopy class of P compose gamma star P compose I of the inverse of gamma prime. This is equal to the homotopy class of P compose gamma star the homotopy class of the inverse of P compose gamma prime. This is equal to P compose gamma star P compose gamma prime inverse. Thus, the class P compose gamma is equal to the class of P compose gamma prime, which implies phi is well defined. So we have defined a map of sets, and the theorem is phi is a group homomorphism. Phi is an isomorphism of groups. So proof. So suppose if the class of P compose gamma is the identity, this implies P compose is P tilde. Is P tilde compose gamma is there's homotopy F, homotopic to the constant loop at x naught. So applying the lifting theorem, we get a homotopy So we apply the lifting theorem so that the 0, 0 point goes to x naught tilde. So this end is x naught tilde. The unique lift of p tilde composed gamma, which starts at x naught tilde, is exactly gamma. The unique lift of cx naught, which starts at x naught tilde, is exactly cx naught tilde. And this forces that on the right end also we have x naught tilde, and this is a homotopy f to x tilde. So this forces that gamma of 1 is equal to x naught tilde. But gamma of 1 is, by definition, we had chosen gamma to be a path from x naught tilde to f of x naught tilde. So this implies f of x naught tilde is equal to x naught tilde. So this implies, by uniqueness of lift, that f is equal to identity. So this implies phi is injective. Well, we haven't proved yet that phi is a group homomorphism. So let's assume that phi is a group homomorphism right now. So we will prove later that phi is a group homomorphism. Let's first prove that phi is surjective. To show phi is surjective, start with a loop. Gamma in the fundamental group at x naught, and let gamma tilde be its lift starting at x naught tilde. Let f from x tilde x naught tilde to x tilde comma gamma tilde 1 be a unique element in odd p tilde then, by definition, phi of f equal to p tilde compose gamma tilde, and this is exactly equal to gamma. So this implies phi is surjective. So let us show that phi is a group homomorphism so let f and g be in odd p tilde. Let x1 tilde be f of x naught and x2 tilde be g of f of x naught. So let gamma 1 be a path from x naught tilde to x1 tilde. Then g compose gamma 1 is a path from g of x naught tilde to g of x1 tilde, which is equal to g of f of x naught tilde. And let gamma 2 be a path from x naught tilde to g of x naught tilde. Then gamma 2 star g compose gamma 1 is a path from x naught tilde to g of f of x naught tilde. Thus, phi of g compose f is, by definition, p tilde compose gamma 2 star g compose gamma 1 is equal to p tilde compose gamma 2. And this is equal to 5g star phi of f. So this implies phi is a group homomorphism. Now the earlier argument shows that phi is injective. Assume phi is a group homomorphism. So this is proved on next page. So this implies that phi is an isomorphism of groups. So this completes the proof of the theorem. So if P from y naught to x naught is a connected cover, then we saw that P lower star in the exercises, we saw in the exercises from pi 1 y naught to pi 1 x naught is an inclusion. This was an exercise. So one can check that using the above isomorphism phi, the Galois correspondence can be written as so from covers of X to subgroups of odd P tilde, which is isomorphic to subgroups of the fundamental group. If you start with a cover P from y naught to x naught, then under this correspondence This cover gets mapped to the subgroup P lower star by 1 by 1. So this is left as an exercise. So finally, we state the following important theorem without proof. So in our entire discussion, we assumed that there is a simply connected cover. So this theorem addresses when there is such a simply connected cover. So before that we need a definition. X is said to be semi-locally simply connected if for every x there is a neighborhood U such that the inclusion induces a map at the level of fundamental groups, then so we want that I lower star of pi 1 ux should be the trivial. So the theorem let x be a connected and locally path connected topological space assume x is semi-locally simply connected then x has a simply connected cover. So this ends our discussion related to the Galois correspondence. So let us now show that homotopy equivalent spaces have isomorphic fundamental groups. So first we have to define when two maps are homotopic. Let f and g be maps from x to y. We say they are homotopic if there is f from x cross I to y such that f restricted to x cross 0 is f and f restricted to x cross 1 is y, is g. So homotopy is an equivalence relation. This is easily checked. And given such an f, we shall denote f sub t to be f restricted to x cross t. So recall that for a path delta from 0 1 to y, we had defined an isomorphism phi delta from pi 1 y of delta 1 to pi 1 y of delta 0 given by gamma maps to delta star gamma star inverse of delta. So we have the following proposition. Let f from x cross I to y be a map let delta of t be the path f sub t of x naught, which is equal to f of x naught comma t. Then the following diagram commutes. Pi 1 x naught f1 lower star pi 1 y comma f1 x naught. Is phi delta, the isomorphism. We had proved earlier that phi delta is an isomorphism. So let us prove this. So let gamma from 0, 1 to x be a loop at x naught. So consider f compose gamma cross identity. So its image in y looks like so. This is the path delta of t. There's a path delta. Let's say this is the point delta of t. This is the point y naught, which is equal to f0 of x naught. And we need to show that so we need to show that f0 compose gamma is homotopic to delta star f1 compose gamma star I of delta. So we will give a homotopy G such that Gt is the loop at y naught indicated in brown. So it's going to be this loop. So we consider the following three maps. So here we have f of x naught comma st. Here we have f compose gamma cross identity. Here we have f of x naught comma 1 minus s into t. So it's t. So let's call this path p1 of t. This path is p2 of t. And this path is p3 of t. Let's call it s, sorry, not t. So the path p1 of s, it starts at f of x0 comma 0, which is f naught x0, and it ends at f of x naught comma t, which is ft of x naught. So the path p2 of s, it starts at f compose gamma cross identity of at 0 comma t, which is f of comma 0 comma t, which is equal to ft of x naught, and it ends at ft of gamma of 1, which is again x naught. And similarly p3 of s, it starts at f of x naught comma t, which is ft of x naught, and it ends at f of x naught comma 0, which is f0 of x naught. Thus, so since the endpoint of PIS is equal to starting point of PI plus 1s, these can be combined to give the homotopy G. So G is from I cross I to Y, which satisfies. So 1 G of s comma 0 is homotopic to C x naught star f0 compose gamma star C x naught, which is homotopic to f0 star gamma. G of 0 comma t is equal to f0 of x naught, and this is also equal to g of 1 comma t, and 3 g of s comma 1 is homotopic to delta star f1 compose gamma star inverse of delta. So thus we get that f0 lower star of gamma is equal to phi delta compose f1 lower star of gamma. So this completes the proof of the proposition. So now let's define what a homotopy equivalence is. So definition, that x and y be two topological spaces we say x is homotopy equivalent to y if there are maps f from x to y and g from y to x such that G compose F is equal to is homotopic to identity X, and F compose G is homotopic to identity Y. So the maps F and G are called homotopy equivalences. So we come to a final proposition. Suppose X and Y are path connected spaces. If they are homotopy equivalent, then pi 1 x x naught is isomorphic to pi 1 y y naught. Proof: let f from x to y and g from y to x be homotopy equivalences. So then we have G compose F is homotopic to identity X and F compose G is homotopic to identity Y. So applying the previous proposition, we get that G lower star compose. So G compose F lower star, which is equal to G lower star compose F lower star, is an isomorphism which implies that F lower star is an inclusion and G lower star is a surjection. So similarly, we get F compose G lower star, which is F lower star compose G. G lower star is an isomorphism which implies F lower star is surjective. Thus, F lower star from pi 1 x x naught to pi 1 y f of x naught is an isomorphism. Thus, the fundamental group is an algebraic invariant which depends only on the homotopy equivalence equivalence class. In the following lectures, we will define singular homology and prove that up to isomorphism it depends only on the homotopy equivalence class. So we will end here.